Today, we're on the other side of the country with Bob Gerber, class of 70, who's based in Maine. He will talk to us about coastal flood mapping, both the technology and the politics. To Bob, coastal flood mapping is effectively modeling, excuse me, environmental systems. Bob was a course one major at MIT, that's civil and environmental engineering, and he earned a master's degree in the field from Stanford. He's worked for both individual clients and municipalities to challenge proposed new coastal flood maps drawn by FEMA, and he can testify to how difficult it was to get the agency's attention and to make them, quote unquote, toe the line. Bob will talk for about 45 minutes, and then we'll open the floor to questions and comments. If you would like to talk, please use the chat function to indicate that. If there is continued discussion, we can keep going until 12:30. So again, please make sure your settings are on mute, and let me turn the floor over to Bob. Bob.
Thank you. Good morning, everybody. Can you hear me all right, Karen? Okay, good. You can hear me. All right, this talk will take about 45 minutes. I'm going to go through it fairly fast. If you downloaded the background materials that came as a link in the email, you had a more detailed talk there that you could have looked at, but we don't have time for the whole thing. But I wanted you to get all the background because this is somewhat complicated and there's a lot of government bureaucracy aspects to this thing. So, now my screen is locked, so I can't seem to move to the next. Oh, here we go. All right. So, the National Flood Insurance Program, it was created by Congress in 1968 because the private insurance markets are starting to dry up. They were having difficulty with excessive losses covering flood risks. So the NFIP was designed to be self-funding, but it hasn't turned out that way. As of 2014, there's been about $20 billion more in claims paid out than there were premiums collected. FEMA is part of the Department of Homeland Security. It evaluates risk by mapping the flood risk in various categories, which we'll discuss today. FEMA has a headquarters office in Washington, D.C., and it has various regional offices. Maine is part of Region 1, which includes the New England states. So there are several different sources of coastal flood risk. Storm-induced ocean surge is really one of the major ones. When there's a major storm moving up the coast, the winds are blowing toward the coast. The winds are creating a shear stress on the surface of the water and literally pushing water and piling up against the coast. In Maine, we have about the severe storms can create up to 4 feet of ocean surge. In Gulf of Mexico, they can create up to like 20 feet. And so it's pretty significant effect. Wave run-up is a very important piece on steep slopes. And that really is the driving force for mapping flood risk in a lot of places. Rising sea level is a factor because, particularly in New England, where we've had, the Pilgrims landed in 1620, they've had a lot of coastal development over time from colonial period on. So people built lower down, but sea level's been rising ever since they arrived. So it's become a big factor. Places that never saw floods 50 years ago now seeing them. And then wave setup is a small component, but it's an important one in the mapping process and one which has been in contention between me and FEMA, which we'll discuss as we go along here. So let's look at sea level rise in Maine, just to look at that one component of sea level rise. This is a a graph on the x-axis is time in years. The Portland tide gauge was operational starting around 1912. And I've got data on here up through 2020. What each of these little squares represents is the mean position of the sea during each of these years. And on the y-axis, we have the elevation relative to just some arbitrary zero bar in the middle there in millimeters. So you can see there's a blue linear regression line running through all these points. That is got an R squared of 0.79. The set of red points in the last 25 years of the record there, with a slightly more steep regression line shown for them, is something that the Maine Geological Survey has interpreted from those more recent data to say that sea level is starting to rise much faster in this area now. But that R squared is only 0.45. Actually, the tidal epoch, which is the period over which National Ocean Service determines the mean tide and the mean low water and so on, every 18.6 years, is affected by more long-term planetary positions and things like that. So you could probably fit a complex polynomial through these points with an even better fit. I wanted to mention too that FEMA doesn't extrapolate into the future sea level rise. When they revise a current flood map, they bring the sea level up to the date of their revision, but they don't say, oh, well, we had, as in Maine, 7.5 inches per century rise over the last 100 years. So we'll extrapolate, because we won't be doing mapping for another 20 years. We'll extrapolate it out for 20 years. They don't do that. Some basic flood mapping terms that are important here. Base flood elevation, or BFE, that is the elevation that is exceeded 1% of the time in an annual sequence. So in other words, if you invert that 1%, it's what we call it it's a 100-year flood. In other words, that's the elevation of the 100-year flood. You normally use that term 100-year because it confuses people. They think, well, we had one 2 years ago, so we won't have one for another 100 years. That's not the way it works, but we'll call it the 1% annual exceedance is a better term. Still water level, that is the storm surge plus the astronomical tide from the 100-year storm. And total water elevation is the storm surge, astronomical tide, plus that little component that I call wave setup, which we'll discuss. Some key coastal flood zone designations. There are A zones, V zones, things we call splash zones, which really are part of the V zones, and then AO zones. And there's a few other ones that are used very infrequently. But the A and the V zones are the primary ones. A zones are zones in which the breaking wave height within that zone is less than 3 feet. V zones, you have 3 feet or greater breaking wave height, and the breaking waves basically can exert a force on walls and buildings and things like that when it comes up against them. So that's considered sort of an extra risk, obviously, because of the force of those waves breaking on the structures. The AO zones are somewhat complicated, and they occur in these hollows or downslopes behind an area where you have wave overtopping. We'll talk about that a little later. The current flood maps look like this. The older flood maps were basically line drawings. They showed the roads, they showed the coastal boundary, they showed streams and rivers, and then they put the flood zones on top of them. But now they're using these aerial photographs, orthophotos we call them. They're going to correct it, so they're spatially correct. And you have these zones on here that are these polygons outlined in red lines. So within each of these polygons, there's a zone designation. And for example, the one on the southwest corner or lower left corner of that picture, that's open water. It's a cove. and it says VE20, which means this is a high velocity zone. Oh, I forgot to mention the difference between a V zone and a VE zone is if it has an E on the end of the designation, it just means that it's been determined by detailed engineering methods as opposed to approximate methods if it's just saying a V zone. So a VE zone with an elevation of 20, the wave, in other words, the water elevation, which in this case is the wave, 100-year wave crest elevation, is 20 feet above mean sea level. And we use in Maine now the NAVD 88 datum, North American Vertical Datum of 1988. So a wave comes in from the southwest here, and where it moves in, as it moves in this cove, it's shedding energy as it shoals and as the cove starts pinching in here. So the wave height drops down to, so the wave crest elevation, it becomes a 13 feet above NAVD 88, but it's still a V zone because it's a greater than 3 feet break in wave height. And then it goes over a ledge at the entrance of the harbor and drops down to an A zone, becomes 11. Up in the top of that picture, you see a AE 15 zone. That is a freshwater wetland that's elevated somewhat above the cove normal water elevation. And that's flooded due to rainfall coming off the side slopes into that freshwater marsh. So that light brown line is important. It's called a wave transect in FEMA terminology because they require that wave transects be used to determine the profile of the 100-year wave as it comes into shore. And then if it's a fairly mild slope, there's a program that's part of that that's added on called the run up 2, which determines how far the waves will run up a slope. If the slope is flatter than 1 vertical over 8 horizontal. So those wave transects in southern Maine are spaced between anywhere from 1,500 to 5,000 feet apart, and they're supposed to be representative of the area that they're drawn on. And the engineer who does the analysis has to determine how to make the transitions between 2 different wave transects. The flood mapping process by which the public gets to interface with the maps that FEMA is producing. It starts out, if FEMA is going to revise an existing flood map, which they call the effective map, they're going to first give, first of all, they do it on a county-wide basis. FEMA maps flood risk county-wide. They map riverine risks separately, and then they map coastal flood risks if you're on the coast separately. But they do them on a county-wide basis. However, they interact with each municipality that's within the county individually. So they'll first provide a work map to each municipality of what their new flood maps might look like. So they get a chance, the people get a chance to look at it and absorb it and start to formulate their questions. After a period of time's gone by, something like 6 months or so, they'll produce a preliminary map. And the preliminary map is going to become the effective map if no appeals are filed, or if appeals are filed and then resolved by FEMA, and then it becomes adopted formally. But FEMA provides a 90-day municipal appeal period to every municipality once they've been introduced to the preliminary map. After if a municipality files an appeals, then FEMA resolves that appeal. They issue a letter of resolution saying they either accept it or deny it. If they accept it, they incorporate it into their map. And then they'll issue a letter of final determination, or LFD. And it says within 6 months, the municipality has to adopt the new proposed map. If they don't, they may lose their ability to participate in the National Flood Insurance Program. There's one other way to revise a FEMA map. And up until the last year or so, I would have said it's only, as far as I know, it's only ever been done against effective maps, but I'll discuss a case where we did it against a preliminary map recently. It's called the letter of map revision, and there are other variations on that letter of map amendment and so on, which is done through the letter of map clearinghouse, which is one national center that FEMA sets up to take applications to revise their existing maps. So the way you win an appeal or get a letter of map revision approved is you have to show that FEMA made an error in their original calculations, provide better data which will change the map. In other words, let's say FEMA had the wrong topographic information or it wasn't detailed enough. You could provide better data, or you can use a more sophisticated method than FEMA used and say, this is a better method, therefore you should approve these maps. Let's talk about some basic wave terms. A lot of FEMA wave characteristics that we use in these calculations of determining flood risk start with deep water wave characteristics. Deep water is an area where the water depth is greater than half of the wavelength. That's what we generally call deep water. And then if it's less than that, it's transitional or shallow waves. So wave buoys are all around the United States coasts, operated by NOAA, and they measure the ups and downs of the buoy movement during wave action. From that, we can determine, using things like Fourier analysis, the wave periods or the dominant wave period. And from the wave period, we also measure the wave height. So you can take any period of time recorded by these wave buoys and do the statistics on it and figure out wave height and wave period. And then from the wave period, we determine the deep water wave length, which is a gravitational constant times the period squared divided by 2 pi. Then we look at breaking wave heights. That's the deep water wave height divided by 3.3 times the cube root of deep water wave height over length, which we call the wave slope. The wave will break in water depths that are, you take that breaking wave height and divide by 0.78, that's approximately the depth of water in which the wave will break. Now, wave heights are decreased as they move from deep water into shallow water. They are decreased by feeling the bottom or shawling. They're decreased by refraction, let's say traveling between two islands closely spaced together, for example. And then there's diffraction, where waves wrap around the down wave or downwind side of an island, or as they come into an opening through a breakwater and then they kind of curve off to the sides. Wave run-up is a function of the Eroded number, and that Eroded number is a function of slope angle on which the wave is breaking. So the tangent of the slope angle divided by the square root of the height of the wave at the toe of the slope divided by the deep water wavelength gives you the Eroded number. On this slide, I've got two different sets of information. Let's go over the right first. Significant wave height. If we look at a record from an offshore wave buoy, let's say we want to determine statistics for a 100-year storm. So we take all of the records they've got for the whole history of the wave buoy. We use some of these different methodologies, Weibull, Gumbel, things like that, that are extreme value type probability distributions, and analyze the data. And so we'll narrow it down to a particular, let's say, storm that was characteristic of the 100-year storm, perhaps. And from that, we might take the highest 2 hours of wave height from that storm. So in that block, the average of the 1/3 of the highest waves would be called the significant wave height. The critical wave height would be the thing we come up from the statistical evaluation as being the equivalent 100-year wave height, and that's approximately equal to 1.67 times the significant wave height. Now we use mean wave height, or the average wave height, again, of the 100-year storm condition here, for determining wave run-up initially, and then we multiply it by a factor of 2.2 to get the actual run-up which is not the 1% highest run-up, but the 2%, not in a time series, but the 2%, because these data are based on empirical data observed, for example, on actual structures on the coast and on wave tank observations and things like that. They have a statistical distribution. So the wave run-up that is used in these 100-year calculations for flood elevation is based on the 2% of the wave height, of the wave run-up, I should say. So the mean wave height that we use to start that series of calculations is 0.626 times the significant wave height. On the left, we have this diagram. This would be, imagine this as being a cross-section along that wave transect I was talking about. So we're looking through the slope. This heavy black line here is the slope of the beach and land behind it at the start of a storm. The dashed amber line is what would be called the eroded profile, because when we do these analyses on erodible shorelines for FEMA's mapping, we do it based on what the likely erosion might be during the peak of the storm. And FEMA has some procedures that describe how to get at that particular number. So to get at that profile. Down in the lower right, we've got a map datum, which is, again, we use in Maine now NAVD 88. The older maps, in the older maps, like 1985 maps, we use the NGVD 29 datum, which has been superseded now. Then we have the still water level, which is the storm surge and the astronomical tide combined. And then we add, to get the total water level on top of that, wave setup. The wave setup, imagine the wave crest is moving in on the beach and it has a forward momentum to it. So as it runs up on this slope, the mass of the wave, in effect, kind of, this isn't the same as wave run up. It's really kind of the mass before or before breaking comes up the slope somewhat. So it's a slight rise in the whole mass of water as it moves up the slope there before the breaking effect occurs. All right, on the top, we see that in this case, this dash red line under with the words wave run up under it, that is actually going to dominate and determine what the base flood elevation for this profile is going to be, because what happens is the wave comes in, it breaks against this steep slope, and FEMA cuts off, if there's a slope or a top of a wall on the top of a hill that it breaks over, it may go up 20 feet over that. You've probably all seen pictures of waves breaking over walls and shooting up 20, 50 feet in the air even, but they cap it at 3 feet above the top of the slope. And then that is going to be, in this case, let's imagine it's 25 feet above mean sea level. Okay, VE 20. So it's a VE 25 zone there. And it carries inland at least through to what's called the splash zone, which is a minimum of 30 feet. And that's also part of the V zone, same elevation. And then it may change depending on whether the slope goes up, the slope goes down, slope is flat. You follow that out further and you may change it into different designations. Over on the left of that top bar there, you see this AO zone. The AO zone is determined on the rate of overtopping. In other words, the mass of water, the cubic feet per second per lineal foot of the wall or whatever, it's coming over that wall. That determines whether it's an AO1, an AO2, or an AO3. The 1, 2, or 3 are 1 foot of flow depth, 2 feet of flow depth, to 3 feet of flow depths coming back over that slope there. And that's tricky to determine. So this is an example of this is actually FEMA's decision tree that they use to determine which methodology to determine wave run up. There are 4 different methodologies that are generally preferred here: run up 2, AC's, TAW, and the shore protection manual method for vertical walls. And then there's a hybrid where we look at a mix between the TAW and the shore protection manual and see which one dominates. But you can see that it's really dominated by the slope, because the slope is the critical first break point here. And that then from the slope, you look at the error bearing number and determine based on ranges of error bearing numbers whether it's going to be one method or another. We don't have to look at the details of this logic diagram. It's one that I actually prepared myself from reading pages and pages of guidelines and specifications that FEMA put out on describing how to determine whether an AO zone is a 1, 2, or 3. They didn't provide this kind of diagram. And I had to read that thing 3 or 4 times. And I said, well, this needs a diagram so that I follow this correctly, step by step, depending on what they're saying here. So I produced my own diagram. I want to talk a little about the history of the remapping, I should say, of maps in York and Cumberland County, the two southernmost counties of Maine. They were originally mapped in 1985 by Stone and Webster. That was the last effective maps. And those maps, incidentally, are still effective in this county, the 1985 maps. But as of 2006, we had now had detailed topographic data developed from airborne LIDAR, which is accurate to about plus or minus a half a foot vertically. We had the ability now to put maps into to a coordinate system that was very accurate, like UTM or Maine State Plane Grid system or whatever. And we had a lot of, fancy new methods had been developed since then. So there were a lot of reasons to improve these flood maps. And so in 2006, FEMA hired some consultants. FEMA doesn't do these re-flood mapping exercises themselves. They administer the process, but they hire consultants to do it. And so the consultants worked on that, and FEMA held some public meetings in Maine and so on, and consulted with a number of agencies and stuff. And then in June 2009, they issued their preliminary maps. And the city of Portland didn't like what they saw on the preliminary map, because the city of Portland harbor zone is about a mile long of wharfs and docks and expensive real estate there that has existed since the mid 1800s. And the city gets a lot of tax revenue out of there and was hoping to get more. FEMA proposed to change that from an A zone to a V zone, meaning, and what happens then is that insurance rates for V zones are much higher than A zones because of the destructive force of breaking waves. And they also raised the elevation of the proposed flood zone quite a bit, so that some of the wharfs would be, in much more danger according to their calculations. So they hired me to review it. I'd done previous shoreline work for the city. I looked at it and I said, well, they've used some pretty simplistic and conservative methods to come up with their approach here. And I said, I could use, without too much more expense, I could use a much better, more accurate methods. And I think their wind velocity, because FEMA basically determines their, wave heights in an enclosed area, and we're talking about Casco Bay here. The wind's coming from the northeast down the length of Casco Bay, which is like 15 miles long. They'd used a simple analytical equation to determine what the wave height would be from this given wind blowing across that, what we call fetch, as it arrives at the Portland Pier, where the tide gauge is actually. And they had a 71 mile per hour, 1 hour duration wind built into that. That's a default number, frankly, in the CHAMP methodology. And I said, well, I don't think it's that high. I've done other work and evaluated wind velocities before as a function of, various return periods. So I went and I did some detailed statistics of the Portland Jetport data and the nearest offshore buoy off Cape Elizabeth, and found that both of them came in, in the 52 mile per hour range. So and then I used a two-dimensional wave model to bring, to start the wind at the north end of Casco Bay and move it down to the southwest. And that also took into account a lot of factors, which I'll illustrate in more detail in a few minutes. So I came up with a much lower flood elevation, and it left most of the areas of the piers inside the ends of the piers to be an A zone instead of a V zone. So at that point, the city wanted to talk to FEMA and say, look, we'd like to appeal this, but we want to talk to you about, the methods we're going to use and the data we've developed from these statistical analysis of the wind. So at first, FEMA had never heard of me. The Boston consultants and FEMA had never heard of me. So they kind of brushed it off and said, well, we're very sure of our process and data. So what we had to do is we got Senator Collins, and at that time, Olympia Snowe, who was our US senators from Maine, to go to the headquarters office of FEMA. You really can't get a lot done politically trying to deal with the local regional office. You have to start at the headquarters office, because they're the ones who can tell the headquarters office to change their approach on something. So they went to headquarters and said, look, City of Portland, the largest and the financial center in Maine, is concerned about these maps, and they think they've got a better way to evaluate the risks there in Portland Harbor. They'd like to have a meeting with FEMA and discuss that. So they went, headquarters office told Region 1 to meet with us. We met with them, and they brought along their consultants doing the work. The consultants looked at it and they said, well, yeah, that looks reasonable. That's probably a more accurate approach than what we use. So FEMA basically gave them the nod, and then 7 more municipalities in Cumberland, New York County jumped on the bandwagon. So I ended up doing 8 different appeals by the time the first appeal period started. But even then, the first appeal period started in 2010. It didn't even get halfway through, and there was so much uproar from not only the ones I was representing, but the other towns as well about the new maps that Senator Collins pressured the DC office to stop the initial appeal period and provide more time to discuss things with FEMA. So although they said it couldn't be done, Craig Fugate, the head of Department of Homeland Security, cut the municipal appeal period right in the middle and said, all right, we're going to go through a new process now. And that's described in some of the background materials I gave you. I don't have time to go through it here, but anyway, long story short, FEMA basically, we trudged along for a couple of years and had a lot of discussion with FEMA, fortunately, because of the new detente. And FEMA issued new maps in November 2013, which incorporated the changes that I made for the 8 towns I work for, and then left everything else alone. So the changes I wanted got put in. The other changes, there were no other appeals that were credible. So nothing else happened. So FEMA placed that 2013 preliminary map on hold, though, because in the fall of 2014, I appealed Situate and Marshfield maps in Massachusetts. And I did that using the same methods that FEMA had said I could use in Maine. Well, the ST wave method was okay, but they didn't like the wave setup methodology I used because I didn't use the only single approved method that's in the guidelines and specifications, which is called the digital integration method, or DIM, which is developed from observation of wave setup on the West Coast. It's also included, though, in the Gulf Coast and Atlantic Coast guideline documents. And it was the only one at the time I applied, really, that was suitable or approved to be used. I didn't like it. I knew that from comparisons of calculated wave setups from the February 1978 storm in Maine, that it was way overestimating this wave setup. And so I had developed a different method, approximate method, that FEMA had gone along with for Maine. But FEMA denied my appeals because they didn't really want me to, although they didn't mind me doing it for Maine because they had the support of the Maine senators. They didn't want me to extend that methodology into Massachusetts. So they said, well, it's not part of the guidelines and specifications. So we're denying your appeals in Situate and Marshfield. At that point, I said, well, all right, well, I want to take this to the scientific resolution panel. That process is an arbitration process that FEMA had just set up within the last year or two. I think I was the second person to go through that process. Basically, you can appeal a FEMA decision using that scientific resolution panel. They have a panel of experts, and you provide briefs and you have a hearing, and then the experts decide what the decision will be. Well, they decided to uphold FEMA's denial because they said the method I used to calculate wave setup was not in the guidelines and specifications, which is true, but they upheld it. At that point, FEMA said, well, I guess we can't use Gerber's maps in Maine anymore, the ones that he's already done using this method. So they threw out the stuff that I did, or most of it. And so they redid everything that I had done in those 8 towns and created new maps that came out in April 2017. Along the way, they decided, all right, well, we'll use the ST wave model, 2-dimensional wave model as well, because that's a better method than our original linear transect calculation from fetch distance for calculating wave heights. So They did that, and I don't think that was the major improvement that they added. And they only did it from one direction. Usually when I did an appeal, I looked at several different directions to see which was more controlling. But by April 2017, I was moving out of an office. I was starting my retirement, wasn't going to work in the office. I was working at Ransom Consulting in Portland. And I had hired a year before that, in preparation for my retirement, so-called, I had hired a guy, Nate Dill, from the Woods Hole Consulting Group to take my place, because he was a very good modeler, better than I was, frankly. And I wanted him to keep taking this into the future, into more and more refined methodologies. So Nate and I looked at this just before I left, and we found a lot of issues with the FEMA, new preliminary maps. Nate decided to solicit some of the municipalities that we worked for in the past to appeal these new maps, and he wanted to use a new process. He developed, he wanted to model using a coupled AdCirc-Swan model, which is a coupled surge circulation model with a wave model. And that is the same process that the Army Corps of Engineers used after they got funding from Hurricane Sandy. Congress gave them the funding after Hurricane Sandy in 2012 to do a very fancy modeling effort between basically Virginia and the east coast of the down east coast of Maine, Eastport, Maine. So they had created a giant model, AdCirc, and they used ST Wave as their wave model, linked to it, and went through a lot of steps. What they did was they simulated 1,050 hurricanes and over, I think, 100 or more northeasters. The hurricanes were synthetic generation. Basically, they took properties of hurricanes known to have occurred, and they generated wind fields, which then generated the wave fields, and had them move up the coast within this model. And they basically chose every possible path along the coast, spaced out, that you can divide it into 1,050 pieces. For the Northeast models, they actually took historical models from the last 20 or 30 years where they had their barometric pressure fields and so on, and then did the same thing of, put that in the model, created the wind fields, the wave fields, and then moved them up the coast. From using some very fancy statistics analysis, from that data, they're able to produce what I'd call, we'll get to that in a second, some exceedance probability numbers, annual exceedance probability water levels with a much higher degree of accuracy than has ever been done before in a very highly discretized setting. So what Nate did was took the NACS study, which is the North American Coast Comprehensive Study, it's called, and you can look that up on the references. I gave you a link to that study. It's pretty fascinating. And he said, well, the NACS study used a very coarse grid, and I need a much finer grid because they didn't take their model into the estuaries behind like Berry Beaches and things like that, which we needed to do. We've got these huge areas like Scarborough Marsh that get flooded, and that wasn't included in the Army Corps model. So he said, so I need to get a more detailed model. So he developed a detailed model from Rockport, Mass, going up to Cape Small, Maine, included all of York and Cumberland counties. And along that boundary, the edge that runs from southwest to northeast of this finite element grid, you see, this triangular finite element grid, he reverse interpolated all of the time steps and boundary conditions from a subset of the NACS modeling of both the hurricane and the northeasters. And then he simulated those within this grid here, calibrated it to some known storm data. There were some biases that were created in some of the storms that they'd done, and then produced a set of statistics that looks like this. So this is for the Portland tide gauge. This is 1 point, but Nate could give you a graph like this for every 100 foot of shoreline from the north end of Cumberland County to the southwest end of York County. On the x-axis, we've got annual exceedance probability. This is water level created by astronomical tides and storm surge. And on the y-axis, we have the elevation of that water level, the storm tide water level. Okay, and Nate's model, he coupled SWAN 2D with AdCirc, which also gives us wave setup is included. Although setup usually isn't felt until you actually come ashore. The tide gauge is out at the end of a pier and has negligible setup. But what you've got at this tide gauge from the hurricane simulations is this red line. From the northeaster simulations, you get this green line, and then the combined annual exceedance probabilities is this blue line. So at 10 to the minus 2, which is annual exceedance of 1%, which is FEMA's storm, that's what the BFE is based on, or 100-year storm in colloquial terms, comes up with an elevation 9 at the tide gauge. And that's pretty darn close to what the February 1978 storm was, which is the kind of storm record for New England, that is considered to be close to the 100-year storm. So to continue on with what happened, FEMA submitted, he did all this fancy modeling, got the towns to pitch in like $500,000. Each of them, paid a percentage of that $500,000 to do the modeling. And then he had to do individual transects within each town too. He submitted the report to FEMA, and FEMA denied the whole works. Every town, all of the whole bloody thing. They said, well, they found an error in Nate's MATLAB script where in one place he didn't make the transition from metric to English correctly. Most of this modeling is done in metric, but you have to translate it to English units for FEMA's purposes because they map in feet, not meters. And in the SWAN 1D calculation, he had neglected to make the metric to English thing. And they found that mistake in his MATLAB script. So they turned the whole thing down, even though that made a very small change. In 10% of the transects, it might have made a 1 foot difference in elevation. Well, the 5 of the 8 municipalities or 7 municipalities that he appealed got together in November 2019, and they were trying to figure out a way to salvage this. They asked me to come to the meeting because I'd had so much experience dealing with not only our FEMA in general, but particularly our congressional delegation and working through them to get FEMA to be helpful to us. So we decided, the members of there were representatives of the congressional delegation at this meeting. We asked them after some discussion to go back to Washington, DC headquarters office, and ask them to let us have another shot at this. That's not normal. You don't get 2 shots at a municipal appeal process. But since so much money and so much work had been done on this, and only very minor errors that occur. In fact, FEMA Region 1, when they denied the thing, said, well, we don't have any real problem with your methodology. It was just this error that we found. So FEMA headquarters said, okay, we'll let you appeal through the letter of map revision process, through the letter of map clearinghouse. I'd never heard of that done before. I've never heard of preliminary maps being able to be appealed before, but when headquarters office says something like that, they make it happen, and they did. So in the last year, we went through that process. Now there was another issue to here, and that was a time thing, because FEMA, having issued the resolution letter, was ready in January 2020 to issue the letter of final determination, which would have only given the town 6 more months. We figured we need about 1.5 years to put 5 towns through the letter of map revision process. So there were 2 towns. Remember, I mentioned there were 7 originally, one in York and one in Cumberland County, that were not part of this 5 people coalition here. We asked them to go through the SRP process, because that basically make FEMA put their actions on hold until that process had been resolved. That process didn't issue a decision until this last October. And FEMA thought about it for a couple of months, and then they said, all right, we'll basically, in the SRP panel, found for Nate and said that his work was superior to FEMA's, and FEMA should adjust their maps according to FEMA, to his changes in those two SRP proceedings. FEMA agreed to do that, and that requires some time and money to revise the preliminary maps. And so we ended up getting basically an extra year out of this thing, which is what we needed. So we've worked through that with the letter of map clearinghouse, and we fixed the little error, which didn't make much of a difference in many places anyway. And we worked through all the issues, and FEMA's clearinghouse has accepted that. So I just want to mention two different issues as examples of the order of magnitude that we changed these maps. So in the issue of wave setup, the one that I had the issue down in Situate and Marshfield about, the SWAN method, the SWAN 1D and SWAN 2D methods were approved basically about the time that I did the appeals down there. I wasn't even aware of them at the time because I had done my work prior to that. But they've been approved, and the wave setup calculated on Wells Beach is by Nate's advanced methodology was 1 foot plus or minus 0.2 feet. FEMA's preliminary map from 2017 calculated the wave setup to be about 4 feet plus or minus 0.1 feet. And in addition, they carried the wave setup over the barrier beach into the large marsh areas behind the beach, which are flooded in these. But Nate's AdSurk Swan coupled model is the type of model that would allow you to carry whatever component of setup would really be carried over into those marsh areas to be reflected accurately. And it showed there was negligible setup in there. So basically we reduced those areas back there by 3 to 4 feet change. And then going back to 2009, when I did the work for the city of Portland, the original FEMA wave height estimate at the Maine State Pier in Portland was the 100-year wave crest elevation height was 9.6 feet, the height of the wave, I should say. I came up with a height of the wave of 4.25 feet using the revised wind statistics and a 2-dimensional model instead of a 1-dimensional model. Just to show you what these, this picture here, this color flood map on the right is depths of water during the 100-year flood. The brown land is the upland areas. They're above the 100-year flood elevation. The red is shallow water in this area here. Casco Bay is outlined by this purple box, and the wind starts up here at the head of Mere Point and blows down. And City of Portland is right in here. This tide gauge that we're talking about is right with my little finger pointers pointing. And so you can see there's a lot of islands and a lot of red. And so this created a lot of refraction and wave energy dissipation on the way down. That's reflected in this. This is a map of significant wave heights generated by ST Wave. And so the lowest wave heights are in the red and the highest are in blue. So as the wind comes down, you can see in the lee of these islands, you have, very little wave height. You get a slight diffraction, bringing waves around the corner and so on. And you get a lot of refraction and wave loss, wave energy loss going between all these islands. There's a lot of ledge in that. Remember the previous picture showing all that shallow water area. So that, this is the combined change in the wind and this type of analysis is what reduced those wave heights in there. Now, I just want to mention briefly there's some social justice issues around this issue of appealing FEMA wave, flood maps. And that has to do with the fact that when we're successful in getting these appeals, we are often reducing flood elevations by on the order of 4 feet, something like that. And we may end up changing a V zone to an A zone. FEMA, if we win these appeals, FEMA basically makes those changes for only those areas that we changed. And if it happens to be a single private property owner, the guy next to him doesn't get a change, just the private property owner that paid me. And I used to charge, I was charging $5,000 to $10,000 to private property, depending on the complications involved, Loma. And for, at the level that I was using, just ST Wave model without the AdSurk surge modeling component, I was charging towns 15 to 25,000 to do their municipal appeals. So when the town, often we didn't do all the transects in a town. The town would say, well, I can only pay for 5 out of the 10 transects, so do 5 of them. And so the ones that didn't get revised by us were left where they were, because FEMA didn't have the money or the time to go back and say, oh, well, we like your work there, and so I guess we'll go back and do the same thing you did for the rest of the county. They don't do that. So what happens is some people that are adjacent to the areas we win appeals for are paying a lot higher insurance than the ones that we got the appeal. There's an interesting article on published in a magazine called Pacific Standard, which has both an online version and a paper version, published every 2 months, I think. In January 24th, 2019, it's called Off the Map, the Problem with FEMA's Flood Maps for the East Coast. And it's built a lot around the appeal work that I have done on the coast of Maine here. And there's a link, I think if you downloaded the background materials, you can click on that link and that's still online. You can read that article. Kind of humorous, I think. So in summary, challenging FEMA maps requires first an extensive knowledge of FEMA's guidelines and specifications. I mean, there's over like 3,000 pages of this stuff. Plus they incorporate by reference things like the Shore Protection Manual, or now called the Coastal Engineering Manual, which is another 1,000 pages in itself. I was pretty familiar with that manual actually before I started this, but I had to learn all the other process type stuff and some other methods that I'd never used before. I had to have the cooperation of Maine's U.S. senators. Fortunately, I actually knew them personally and actually had done private work for one of them. So they knew me, they trusted me, and they went to bat for me. I needed clients willing and able to pay the costs. These things aren't cheap to appeal. And I needed the knowledge and ability to apply the advanced modeling technology. Thank you to MIT for some of that. And the knowledge I picked up along the way from the tools I learned at MIT. And then I needed a long-term perspective and perseverance. I started this in 2009. We're still working on it, trying to get a new map in here in 2021. It'll come along in July of 2022, finally. I was the main driver and the one who kept hanging on to this. Town managers would come and go and different towns would lose interest and things, but I kept going. And as a result of my persistence and then hiring a good replacement for me, who's even better than I am at this stuff, this sequence of challenges forced FEMA to basically up its game and improve its methods. So that's the talk. And I want to leave the rest of the time for discussion, and I hope if you've read the background materials, that'll provide you even more information that you might want to ask questions on. That's fine.
Thank you, Bob. I know a lot more about modeling and about reaching out to senators now. Let me ask one question, and then I will turn to the people who have put their names in chat, and I encourage others to do the same. So you grew up in Maine.
Yes.
Did you ever do science experiments or related to this, or envision yourself doing things like this when you were in high school or a student?
Well, I wanted to be an architect, and I actually got applied for and got approved for the MIT 5-year bachelor program in architecture. After the first year of civil engineering, I had to take 2 freehand drawing courses as part of the architecture curriculum. I found I can't do freehand drawing very well. It was very frustrating for me. So I switched to civil engineering, which I could use straight edges and French curves and things like that. So, but I've always lived on the coast. So I've been an observer of wind and wave conditions. I've been a boater, a sailor. I've basically been involved on the coast my whole adult life. And actually childhood life as well. So
thanks. Okay, turning to our audience. B.D. Nyack, unmute yourself, please. Are you there?
Hello. One thing. My video is not working here. My question was regarding any actions taken recently to protect the coastal areas in the Maine area.
The actions to put the what into the main area?
You can look in chat if you want to see it written.
Maybe that'll help.
Okay. Here I am.
I'm trying to find, which one is it?
Go, let's see.
I got to go up to the top.
First one.
Oh, I
What
got
is the most
okay.
recent action, if any, that is taken to prevent New England coastal area from rising? I think to
That's a good
protect maybe-
question. I
yeah.
don't, there's been a number of actions done by different governmental entities. I know Boston has used that NACS model to try to plan how they're going to deal with rising sea level. In Maine, I can speak a little more specifically from Maine. Maine set up a commission, the legislature, a fairly large commission about a year or so ago to study the effects of sea level rise and come up with strategies that they could implement legislation on or develop regulations to control things. Mostly the actions that I've seen so far, the city of Portland, for example, has been raising, literally building up higher some of the roads in their low-lying areas around the waterfront. That's one concrete action they've taken. The buildings are still where they are, but the roads are a little higher. Different towns are taking different steps. There's some towns are building or proposing to build breakwaters. Of course, there's a big emphasis. I've done some planning work for some towns where I've basically said, these buildings are going to be at risk in the next 20 years. You're going to have really significant problems here. In fact, I told the city of Portland that I was able to get a letter of map revision for their harbor zone there. I said, this is only good for like 20 years. And then you are going to be in a V zone. You are going to be in higher water levels. And this wharf zone is going to be underwater. You need to plan for this. So the town of Stonington, which is mentioned in that article that I referenced, I actually chose a piece of vacant land for them on higher ground and said, I would suggest the town buy this land and start seeing if they can move some of these people that are on the waterfront. They're going to be in great danger up into this piece of land. So those are the kind of things we're talking about.
Thanks.
Okay.
Kaya, you put in a reference to something. Do you want to speak now and talk about that, or?
Well, I meant the reference I was talking about was that magazine article.
Ah, okay.
You can read about Stonington in that article.
All right, we can come back to Kaya then. He does have a question later. Roger Chang.
Oh, hi, Karen. I didn't have a question per se. I just wanted to point out that FEMA is just in the process of releasing Risk Rating 2.0. And someone earlier had posed a question on New England coast. Massachusetts has actually produced a pretty good guide in 2018 on how to address climate resiliency and sea level rise.
Have you worked with them?
I actually work with FEMA. I'm the Deputy Director for Hazard Mitigation.
Thank you. Roger
This
Chang.
is Roger Chang. Hi, as you were talking, you got me all stimulated. I started researching the addresses. I've got 2 properties on minimal floodplain, and I've got one at a 0.2% flood hazard. Is 0.2% bad?
That's the 500-year floodplain. Well, it means that, they've definitely defined a risk level there. It's less than the 1% risk. But if in the coastal zones, at least in Maine, we haven't defined that particular risk level, but in riverine areas, they have. And in the riverine areas, we have a lot of rivers with gauges that have got a bit 100-year or more of gauging data that they can basically feel confident about designing that kind of probabilistic level. So it's some risk, it's some, but not as much as if you're in the an A or a V zone or something like that, you know.
Yeah, I've noticed that I'm in Maryland, and these properties are in Florida. And I watched the videos of Ellicott City a few miles away from me, and the just because of the river and the structure, and these cars being washed down the streets,
Yes.
and people, getting carried away down there. It's has a lot to do with the topology of the area, besides just how close you are to the ocean.
Oh yeah, it does. I mean, the riverine risks are evaluated with different types of modeling technologies like HEC-RAS and so on. I have done some riverine work, and I've even appealed some riverine maps of FEMA's in the past, but it's a different thing. But basically, yeah, people don't realize, even in very flat areas, and they may be high and dry and think they're fine. Well, look in the Houston area. I mean, what's happened in several major rainfall events in Houston, it with the increased development, the impervious area that's being created, and increased, it seems to be that climate change is creating storms that have an increased frequency and higher intensity. In Maine, the intensity of the 100-year storm is, let's say, the amount of rainfall in a 100-year storm, 24-hour period, is now estimated to be 25% higher than what we calculated back in the 1960s.
That's huge.
Yeah, it is. It really changes the whole picture.
Yeah, I've been out in the deserts of Arizona, and they said, don't go into that riverbed.
Oh, yeah, and that's a different situation. It's because the flood occurs way up in the mountains, and you don't even know it's coming until it falls.
Until you're gone.
Yeah, right.
Okay, thank you.
Thank you.
Robert Oppenheim. Unmute. If you're still there.
Here we go.
Good.
My question was this: you have settled maps for a flood zone in a particular area. All the appeals process have been resolved. Along comes a storm and the projected flood area is overrun. What happens then? Does FEMA basically say there's a problem with the way we calculated the maps? Is it chalked up to a 1,000-year event and forgotten? Do you scrap methodologies? What do you do?
Well, there's two basic things that happen. I think they're happening for example, in the Long Island Sound now as a result of Hurricane Sandy. I mean, that storm was created flood levels way higher than anything had been predicted. The surge elevations were enormous. And the coasts of the North Shore of Long Island, the coasts of Rhode Island, Connecticut in particular. The first thing they try to do is figure out what was the return interval of that storm by redoing the statistics. They try to figure that out. And the second thing they do is they remap the thing as soon as they can. I'm pretty sure Connecticut's undergoing remapping right now, even though it had been mapped fairly recently before the Hurricane Sandy. So those are the two things they try to do.
Okay. Lou Metzger, sorry I skipped you.
Yeah, hi. Just wondering, it sounds like you're talking about more accurate modeling resulting in a less conservative result. But don't we have a risk of being less conservative than we ought to be unless FEMA also starts extrapolating the sea level rise?
Yeah, in fact, in talking with a number of town managers when I was trying to get them on board to do appeals, some of the town managers said, well, I'm glad it's conservative. Let's leave it the way it is. I don't want to challenge it because I want to have some fluff in here, for the future. So that's one point of view. My point of view was, well, I want it to be as accurate as possible. If we think that we're underestimating the storm frequency or wind velocities or things like that, we can check that. But let's at least make the process as accurate as we can. But yeah, your point, I understand your point. And as I say, there's a number of people that I've talked to that want to keep their maps, assuming they are conservative, for the very reason you're saying, well, we've got rising sea level, increasing storm intensities and frequencies. Let's leave it the way it is and provide some room for mistakes in here. I'm trying to just refine the methods and make them as accurate as possible. And if it, basically, if it reduces some of the conservatisms, it can be dealt with in other ways by making the storm intensities more accurate or something like that. It is a philosophical question, though.
Well, I have sympathy to try to get it as accurate as possible, but if you're going to go for as accurate as possible, don't you also need to take into account the increased slope that you showed us? You know, even though the R squared was relatively low, it's probably really happening.
Yeah, I'm not going to debate whether that's happening or not. I just don't like the statistics there. But but I mean, it has to do. FEMA would have to basically change their methodology to say, all right, we're going to include within our modeling an assumption that one, it'll be 25 years before we do the next mapping in this area, and therefore we're going to assume a sea level rise based on the recent rate of X amount. If they make that policy change, that would be one way to deal with what you're talking about.
Okay, thank you.
Bob, either you or your materials said that FEMA in fact was 20 billion and the government are 20 billion in the hole in terms of insurance coverage for flood. Can you separate Maine? Is there any indication of whether FEMA gets certain insurance right in some places and wrong in others, or is it sort of just across the board?
Well, I'm not an expert in those types of numbers. I'm really the technical person. But I mean, from what I've read, the Gulf Coast and Florida are the big people who take the money, most of it. I don't think there's been that many losses on the Maine coast. From what I know, there has been some in southern Maine. The Camp Ellis area is notorious because they're having very rapid erosion of the shoreline there. But I don't think we're taking the big chunk of their money. That number I gave you was through 2014. I really don't know where it is now. And of course, FEMA they've spent trillions of dollars on beach nourishment. They've spent another 40 or 50,000 on what we call 40 or 50 billion, I should say, on mitigation strategies. For example, after Hurricane Katrina, spending a lot of money down in Louisiana, particularly New Orleans, and improving levees and pumping stations and things like that down there those are called mitigation things. They're not the same as flood insurance, but they're trying to prevent future problems from occurring. So they are putting a big emphasis on mitigation these days. And you can get towns can earn reduction in insurance rates for their residents if they do certain things. There's a certain scale that they can earn points on from FEMA. And if they do the things they ask, they can get reduction in flood insurance premiums.
Thanks. Dave Rainey, unmute. You still there? I can read his question.
Yeah, I can read. I see the question.
Okay. You want to read it out loud so everybody?
Yeah. Should Congress pass an NFIP reform bill to allow or mandate FEMA to incorporate sea level rise projections, use better methodologies, and address social equity issues? Well, that's a political question. They have been. There was the Biggert Waters bill back after Hurricane Sandy, and then where they were going to make for example, insurance rates more actuarial based. In other words, increase the rates, because it's pretty widely recognized that at least coastal flood insurance is there, people pay less premiums than really reflects the risk involved in those. And then so they came up with this new thing and said, well, within 4 or 5 years, you're going to be paying the true flood insurance premium you should be paying. But then the next year there was a hue and cry from a number of influential coastal property owners. And in the next year they passed a bill called the Homeowners Flood Insurance Affordability Act of 2013 that knocked that down again. So there's a pretty powerful lobby of coastal property owners, I'll say that. Whether they should, do that, I don't know. I mean, it's, and, getting stuff through Congress of anything these days is beyond my ability to predict or say what should happen, because it's a difficult place to get anything done, it seems.
Maybe you can use your relationship with Susan Collins to encourage her to do certain things. So, Larry Banks, you there?
Okay, he says our second home is in Harpswell, one of the 8 towns involved. We've been following this for the whole time. Thanks, Bob, for helping to understand the truth. Yes, Harpswell's been a client of mine for a long time. And they were one of the driving forces in going back to FEMA in 2020 and asking them to let us have a second crack at appealing the maps, the 2017 preliminary maps.
Okay, Mike Thiel, you there, unmute.
Okay, he's asking about the repetitive flood loss issue. From what I know, I think it is, and I know there's someone on here from FEMA, he probably could correct me if I'm wrong, but I'm pretty sure now that after you've been paid for one large flood loss, let's say, if the next second loss is 50% or greater than the appraised value of the home, you're going to lose your flood insurance after that. So I think steps have been put in place to prevent this business of people collecting 4 or 5 times for, total losses to their house.
I would hope so.
Yeah, I think that there's an end to that now.
Thank you.
Okay, that was Mike. Steve Mullins. Unmute.
There we go. Hi, Bob.
Hi, Steve. He's a fraternity brother of mine.
Ah,
Yeah, well, it was a brief comment. Didn't expect to ask a question, but that was a great talk for people like myself who know virtually nothing about the flood risks in coastal areas. But I have family in Houston, and of course, I live in Portland, Oregon now, a continent away from your Portland, and we're very concerned, of course, with coastal erosion and flooding here, but as well, we have the additional risk of tsunami, and in particular the subduction zone earthquakes. So
Yeah, the tsunami risk is a whole different ballgame, but it's definitely a risk that, as you say, in that Seattle area and the Hawaiian Islands, it's a big factor. And I haven't been involved in any of that, so I don't know how they evaluate the risk of that, frankly, or estimate I don't know whether the flood maps they produce include that or not. I just haven't been involved in any of the tsunami type things.
okay. Pete Denton.
Yeah, I see that the question, he's correct that the federal flood insurance is limited to $250,000 on the structure. And you get another, I forget, it's on the order of another $100,000 or $200,000 for contents. That's correct. And a lot of the people that I've worked for and done private single landowner LOMAs for, letter of map revision applications for, own houses that are worth $1 million or more. And they pay, and what happens with these people is they buy excess coverage insurance from, and a common source is Lloyd's of London, for example. I had one guy who had a mortgage, his mortgage was $1.3 million. And he was buying Lloyd's of London insurance $20,000 a year to cover the excess over the FEMA level.
Does the private require that there be FEMA coverage first or anything, you know?
I don't know that, since I don't have a house worth that much, and I have never, I don't know.
Do you have FEMA coverage and has it gone up?
I don't live on the shore anymore. I can see it from where I live, but I can't, I'm not on it. I'm well above the flood level, frankly.
Okay. I think we've run through listed questioners. Anyone else have a comment or a question that they want to make? Let's see. Tom Mikas has a comment. Secondary insurance required FEMA first. Okay. Mike Thiel has a comment about Rye, New Hampshire. Mike, you want to make it verbally or people?
I was just thinking, Bob, it's an interesting talk, relevant to me because I own a piece of land that as waters rise and storms get bigger will itself turn into an island. Luckily, my house is high above the water, but I may have to build a bridge to get to it.
Yeah, I have some friends that have that situation. I know what you're talking about.
Yeah. Anyway, thank you.
Thanks. Anyone else?
Yeah, Karen, Pete Denton here, if I could ask a question verbally. The earlier slides in this presentation, I think indicated that the sea level rise in the Portland area were between maybe 1.5 and 4.5 millimeters per year. And that's sort of order of magnitude of 1/8 of an inch.
Yeah, I mean, that's an average number, as you saw. Let me just check that, make sure I'm agreeing with your evaluation. Oops. These averages like that are, as you saw in the data, there's quite a bit of scatter from year to year in the data. That's interesting. So it's one of those things that the averages don't mean a lot as far as I'm concerned. It's really of a thing that's more. We're looking at the long-term average is like it says, like 7.5 inches in the last 100 years, and they're saying now that it's coming up faster than that, maybe double that rate now. So we'll see. I had to do some work out for the a nuclear power plant in Southern California, where I was doing groundwater modeling, but one of the issues was we had to also estimate the erosion rate of the land moving inward, which would basically the sea was going to come up against any structures we left in place, even down deeper over some period of time. And there's a number of different sea level rise scenarios, as you probably know if you've ever read any of these climate change reports. So I had to evaluate it against 4 different sea level rise scenarios. It changes, the groundwater profile behind the beach and things like that. So I worked in conjunction with a group of academics that were a consulting group that did the actual estimates of the erosion that would occur over the next 125 years. And so you do have to take those types of things into account. And
So 2 specific follow-ups. You just talked about 7.5 inches per decade, maybe it's twice that, 15 inches per decade. Very rough order of magnitude, we're talking about 1 inch a decade. Now, I spend a lot of time and have a house on the water in Newport, Rhode Island. And I would say the general population in Newport thinks sea level's going up 1 inch a year, not 1 inch a decade. Now, is the data that you have from Portland reasonably accurate for every place else in the country? Do you think it's less, more? Is it indicative of other places?
Well, I can tell you what the scientists who are studying sea level rise in the Gulf of Maine, that's that area incorporate, north of Cape Cod, going over to Nova Scotia, and then all the way northeast up to, the end of Maine and into New Brunswick, Canada. So that's the area that I know the most about. They say it's rising faster than 98% of the rest of the water body, ocean water bodies on Earth. And I don't know if that's true or not. I'm not involved in those studies. As you saw in that scatter graph, there's a lot of difference from one year to the next in the mean sea level. Of course, that takes all of the gauge, I think the gauge stations, I can't remember the increment of time it records the water levels, but it's pretty close, it's pretty small. And so they take all those and average them to get a mean for the year. And that's what the dots are that's on there. But from year to year, they change quite a bit. And that's going to reflect a lot of different factors. But I don't know. They say Gulf of Maine is increasing very rapidly. And it may, and if you look at the curves, all of the sea level curves, they aren't a linear curve. They're an exponential curve. The curve is going up in time. In other words, the rate of increase is increasing per unit time. So that's one of the factors you've got to think about. And that's the one that's in most question is what is that acceleration parameter, if you will? What is that? If it were just linear and we knew it could be linear and going to stay linear, that'd be one thing. But it's what's the acceleration factor in the rate of rise? That's the big
think
question.
the weather news keeps reminding us of the changes. Anyway, thank you very much, Bob, for a fascinating talk. Thank you to all the people who came and joined us, and to Cardinal and Gray for hosting us, to Nancy Mims, who is the staff person who handles us, Rick Lufkin, who heads Cardinal and Gray, Jesse Hines, who is our class webmaster and helps with tech on this. And don't forget that a month from now, actually, it'll be more like 5 or 6 weeks, we'll have sequoias, and stay safe. So thank you again.
Thank you, everyone. Thank you.